polling's open. And a friendly reminder, I've written it on the board several times. I've sent an email out. I'm not writing it again, but there's 3 of you that are still coming to class, participating in clicker questions, and have not told me that that's your device ID number, because you're not getting credit. So a friendly reminder that if one of those device ID numbers is yours that I've written up or emailed the whole class, you won't get credit until you let me know that's your device ID number. If you're concerned, email me anyway. You can come see the numbers afterwards. All right, so this one has 2 tubes. One's with fresh water, one's with salt water. They're filled to the same height. Does that have an effect at the pressure at the bottom? If so, which one has the greater pressure? Ten, 9, 8, 7, 6, 5, 4, 3. You still entering your password, Candelaria?
Yeah, I have to put like a 6 password, Professor, to get in.
That is weird. I still don't know. They're not playing with Windows well for that platform phone. Tell me when you've got yours. While I could stall a little longer while other people show up. Anyway, yes. And are you on Uconnect or a data plan or something? Okay. If they don't work and you're here, you can write your answers down on a piece of paper and give it to me at the end. I won't, because their technology isn't working, I won't penalize you. Have you submitted any tickets to ResponseWare ever about these issues? The 2 of you that aren't listening to me that this applies to? All right. Your superhero paper. I wanted to say it anyway, so I'll just stall a little longer. Your first thing that's ever due, well, your deadline for the first thing is next Friday. So you only have 1 more week. I would encourage you to do this, not wait till Friday, but you can just email it to me if you forgot. All the instructions are there on WebAssign under the resources. The first thing that's due is your topic. What fundamental physics principle are you going to address? What's your superhero going to be? And a list of the majority of your sources. It does not have to be a physics topic that we have covered yet or will cover. It can be any physics topic. I just want you to start thinking. And worst case, I don't encourage it. If you change your mind later, I'm okay with that as long as you tell me the new stuff, and then I can see that you're going to be okay. I've just run into students that, I don't know, and they go to write the paper. They have this great idea, they think, and they go search for information, and they can't find any, and then they're hosed. So I just want to make sure you don't fall into that trap. But to get credit, you got to at least tell me something by next Friday. Again, you can just email me those things. It's sufficient, or tell me next week in class or something. All right. 2/3 of you think it's salt water, and you're absolutely correct. Why? Because it's more dense. That's right. Pressure was density, gravity, height. I harped a lot that pressure is depth dependent. So if we made those tubes taller and filled them up higher, we'd have more pressure because there'd be more on top of us. But it also matters what's in the tube. You put something more dense like salt water, it's heavier. There's more mass for the same volume, so it'll be heavier. It'll exert more pressure on that area. Mercury, which is really dense, made it so you didn't have to be as high to create the same pressure. In other words, if you had a tube full of mercury and a tube full of water, how tall would the water one have to be 1 atmosphere of pressure? You may remember, we've discussed it and it's in the book. How tall would a tube of water need to be so all of it would create 1 atmosphere of pressure at the bottom? Good, 10 meters. And in reality, if you had that case, it would actually be 2 atmospheres there, right? 1 from the water, 1 from the air. But you get my point. Mercury would be a lot shorter. A lot shorter because it's more dense. I think it's like 760 millimeters. So less than a meter. All right. Let's do another one for learning. 14. Go. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Oh, most of you think B. I feel good. That is correct. So, yes?
So, if the ship is on salt water, technically it should be floating a little bit higher, right?
That's another great question. I'm gonna pose the whole class. Let's say this same ship, it was floating in fresh water compared to, and then moves to salt water. Yeah, how will it be floating different? Higher in the salt, lower in the fresh. Why? Yeah, it's more dense. Or look at it this way. The difference between the density of the fluid and the ship is less with salt water. So it can't have as big a buoyant effect. So yeah, it will shift how it floats. But what do we change the weight of the ship? It's still 20,000 newtons, whether it's in fresh water or salt water. So what's it take in terms of a buoyant force to counter that? 20,000 newtons, no matter what fluid it's in, if it's going to float like a ship. Now, the salt water one floats lower, right? Higher, right. No, wait a minute. Brain fart. You know, sometimes you just get in front of class, right, and you brain lapse. I can't even, I just forgot what the heck that stinking formula was. There it is. DBG. So see, it happens, and that's one reason I don't mind giving you a cheat sheet. So the buoyant force was the density of the fluid, the volume of the displaced fluid, times gravity. Buoyant force is volume dependent, right? So, yeah, if the salt water is more dense, is another way to confirm, then that will create a larger buoyant force. If it's creating a larger buoyant force, is it displacing more liquid or not?
I think it's less because less of it's submerged. So the volume, in a sense, is less than it would be if it were lower in fresh water.
The volume of the part underwater?
Exactly.
Yeah, I think I said it wrong myself too. So our guide to thinking. Salt water is more dense. Just numerically, that means it's got to have a larger buoyant force. comparing the density of the two. If it's less of a difference between the boat and the water, it shouldn't have as big an effect. So it should be down further, lower, like this. It's going to sink down in the water and displace more volume. That greater volume of water displaced can help create that larger buoyant force. Yeah. So two things are going on. We've changed the density of the fluid, but we've also changed the volume of the water that gets displaced because it rides in the water at a different level. Does that help? And I think I fixed myself from saying something wrong. So the point with this one, it's still, the buoyant force needs to be the same as the weight of the ship if it's going to keep it up. Questions? It's good to think through these things. Practice. The more practice you get, you assimilate it. Then you'll do better on the test, right? Go ahead.
I'm still like confused there, because like, so the buoyant force is dependent on the volume, isn't it?
Yeah.
Not depth. Pressure dependent on depth.
Correct.
So.
Correct. They're dependent on some other things too, but the reason I pointed this one out was like, if the dam holding the ocean back, if you're 100 meters down, it's the same pressure whether you're holding the entire ocean back at 100 meters or just a lake. Because the pressure is just due to how deep you are, not how much of it you have. But the buoyant force doesn't care how deep you go. Once you're submerged, if your volume can't change, like a hard shell, a submarine, if your volume doesn't change, and you just kept going down and not changing it, you're still displacing the same amount of water at any depth. So you'll still have the same buoyant force.
But a ship that isn't all the way submerged?
A ship that's not all the way submerged, the buoyant force is dependent on this volume of water that's displaced. The weight of that water is the buoyant force. That's Archimedes' principle. If you change that, you change the buoyant force.
Okay, so wouldn't salt water make it so it floats less, which would change the volume?
But we've changed the density also. So there's two things going there countering each other. But you don't even have to go there, because if the ship weighs 20,000 newtons and you're going to keep it up, the buoyant force has to be the same. They have to equal. So, more simplistic, I think this is easier to understand, which convinces you this has to stay the same. If that's staying the same, and the density goes up, the volume goes down. To keep that the same, to keep it floating. There's some point where you can increase the density enough that the thing won't float. It'll capsize and sink. But I wasn't going there. Good. Feel better? I like the discussion. That's what I was hoping these questions have that effect. So, all right. We already answered that. 32. See, that was my next question. All right, go. And this follows along with it. A balloon is not rigid. That's my clue. Take a balloon down, pass it around. Yeah, well, technically any increase in depth, but yeah, go down a mile, make it conspicuous if that helps you. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, minus 1, up. Guys aren't sure. Well, let's let yourselves talk to each other. We'll ask it again. I'll reopen the polling. Discuss it. Try to convince your neighbor why you had the answer you did. If your neighbor has the same answer, find somebody else. Help yourselves out. Seriously, move around if you have to. Try to convince someone. It'll help you. What do you think?
I'm thinking it's less. That's my first thought. But then
Why?
I'm thinking because the pressure of the water is more and you get deeper, so that'll, since the balloon is rigid, it'll shrink it.
Okay.
But I'm just thinking, would that be proportional to, like, since there's less pressure, like, is it proportional to how much it displaces, like the size? That's what I'm thinking. But I'm still thinking.
Is what proportional to how much it displaces?
The buoyant force.
Is it?
Yes.
There you go.
So it would be the same then, or not?
If the volume changes, so would the buoyant force.
Oh, got it. So it's never gonna try and fall out.
Let's find out. 10. No, a balloon is a balloon. It's not fixed. It's not rigid. Which was my clue from the beginning. A balloon can easily change size. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Get your votes in. Come on, come on. Hurry up. 3, 2, 1. Fine, you're taking forever. Well, it did shift. We got more on A now, but not as many as I would have hoped. It does become less. As you go deeper in the water, name one thing you know for sure happens. Pressure increases. Okay, good. Because pressure is depth dependent. So if you're deeper down, the pressure is greater on the balloon. Will that have an effect on the balloon? What? It'll squish it. It'll take up less space. Will that change something? It'll change the volume of the water it's pushing out of the way and displacing. So it's displacing less volume of water. And then what effect does that have? Less buoyant force. Because buoyant force is proportional to the volume of the displaced fluid. Is anything else happening that we need to worry about to counter that? It's still water, so we haven't changed the density of the fluid. We're still on Earth, so gravity hasn't changed. You were thinking what?
It's cold.
Colder.
It contracts when it's cold.
Air, there's a change in density with air between hot and cold. This is in water.
Yeah, so the water would make the air in the balloon colder.
The colder water would make the air in the balloon colder, which would make it contract even more, which would make the buoyant force even less. So at least it still agrees with our let become less. And that would happen. It's a smaller effect, but very good thinking. The pressure will decrease the volume more than the coldness, but you're absolutely right. So 2 cases, yeah, it's less. It's just because the balloon can shrink from the added pressure. It's now not displacing as much fluid, so there's less buoyant force. Again, somebody's brought this up before. Here's our balloon, let's say. If we're in a fluid, the pressure down here is larger than the pressure up here, correct? Because it's farther down. There's a difference in pressure. It's that net difference that causes this buoyant force. Now let's go even deeper in the atmosphere. Now the pressure here is even greater than it was before, and so is here, but there's still a difference. This has the same height, so it's the same difference. That's why the buoyant force does not change with depth, if the thing keeps its same volume. But a balloon smushes.
Assuming the balloon is adequately sealed, is there a pressure, is there like a depth of water that would be deep enough to the point where the balloon could not contract anymore?
You go so deep that the balloon couldn't contract anymore.
Yeah. Like just
Well, as you kept going and going and going, the pressure would just increase and increase and increase.
yeah, but the air would still be there if it's sealed completely. So
Yeah,
that's just
you can't get rid of the air inside the balloon.
no.
And as you try to, well, it's like this. This has air inside it. And as I try to compress it, it gets harder and harder and harder. The air inside is at atmospheric, well, let's just say it's at a certain pressure. As you increase the pressure out here, that causes the volume to shrink. But it compresses the air, and at some point the pressure in there will increase a little as you try to compress it, and it'll fight. But if you can keep increasing this pressure, that you can keep overwhelming this. But it would never be completely smushed because you could never get rid of all of the air.
So would it be like an infinite kind of decimal kind of thing? Or
Yeah, it'd be really small. Like, you could pretty much smush it and it would look flat, but the air's still there because you've compressed it so much. But you're right, you can't get rid of it. And that's Boyle's law, by the way. It's another thing I wanted to cover today. Those of you that have read that in your textbook, without a change in temperature, Boyle's law is if you increase the pressure, the volume decreases. And vice versa. I'll write it on the board later, but the product of pressure and volume in one condition has to equal the product of the pressure and new pressure and volume. So if you increase the pressure, the volume will go down to keep that constant. I'll do that again once we finish the clicker quiz. But that's Boyle's law. I'm going to do it with this too. I'll just wait till we turn the lights on. You had a question, Stephen, too.
Oh yeah. So with buoyant force, the reason why it doesn't change is that so there is a change in pressure on the bottom when it goes deeper and deeper.
Yeah, there is a yeah.
Change on the top is equal, equivalent, so therefore.
The difference between the pressure here and here stays the same at any depth.
Okay. So that's
When you're deeper, both pressures are greater, but the difference across the object is still the same.
okay, and that's why it stays the same for us.
And that's why it stays the same. Again, assuming the volume doesn't shrink. But a balloon clearly shrinks. So take the reverse. The hot weather balloon, as it goes up in the atmosphere, that's like bringing our balloon back up. What's it going to do? Expand and displace more air. The difference in our atmosphere is we have a second thing going on we mentioned before, and as you go higher, it's less dense. There's less air also. In the water, that doesn't change as much when we went down. I was trying to keep it simpler. Good. And I think I had one more. Yep. There it is, hiding. Okay. Hydraulic press review. That's that force area thing. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Most of you see as the distance. You're right. It's a simple machine. You never multiply energy. You can't create energy out of nothing magically with a machine. In reality, you never get 100% out to what you're trying to put in. A hydraulic device is a machine And if you increase the force by 100 on one side, you're going to have to move it through a similar change in distance on the other side to keep things energy conserved. You can multiply force or distance, if you want to look at it the other way, with a machine, but not energy. Questions on that one? Okay. Done with clickers. Thank you very much. So Boyle was another scientist. It was his last name. Those of you that remember your chemistry with your ideal gas law, it comes from that. This is one of the steps that they use Boyle's law to put together the ideal gas law. But we're just simplifying the ideal gas law, and it's pressure 1, volume 1 has to equal pressure 2, volume 2, if you keep the temperature the same. Those of you that, PV equals nRT is the ideal gas law, if that helps you, remind you. And so these are both constants. So if you keep the temperature constant also, that just means this has to equal, it stays constant. That's Boyle's law, that relationship. And we see it a lot. We just had an example, and I'll give you another example. This is a bell jar. There's a certain pressure in the balloon, certain pressure in the bell jar. You got a vacuum pump. I'm going to start pulling the air out from the vacuum or the bell jar. That'll decrease the pressure. What should happen to the balloon? So that equivalent, that's like me taking it up in the atmosphere. If you decrease the pressure on it, now the greater pressure in the balloon is winning, and it expands. So that's like we had a certain pressure and a certain volume initially. If we decreased the pressure, the volume went up. It's that simple. And the same with these balloons going up in atmospheres or down underneath. It even works with a styrofoam cup. Styrofoam like traps a bunch of little balloons. It's like a little bunch of air bubbles. Scuba divers have taken styrofoam cups down deep enough, and it's compressed the bubbles, just like our balloons. The thing is, with styrofoam air cells, they don't rebound like a balloon. And so when they get back up to the surface, the styrofoam cup is still small. But it's small in all dimensions because the water can get inside the cup and outside. So the pressure is pushing from all directions, and the cup just shrinks. It doesn't collapse, it shrinks. Here's a fun way to kind of do this, a similar thing. Shaving gel. What's it made out of? A whole bunch of scary chemicals and air. So we pump on it. Same thing happens. Those trapped air bubbles are expanding. And expanding. And expanding. And I stop before it goes into the pump. Drop the pressure on them, their volume increases. Now these cell walls aren't as rigid as the latex rubber of the balloon, so if I let the air come back in and increase the pressure on them, they shrink and actually collapse. Ready? Now my bell jar will smell nice and clean after I wash that out. So that's Boyle's law. Let's do a couple more atmospheric pressure demos. Let's do a barometer. Where did I put it? Here it is. Okay. Barometer is an instrument that utilizes everything we've discussed so far. Okay, so here's some blue water. Did I use this in here already? Get confused. I have used this demo this semester. I just couldn't remember where. So the pressure here is atmospheric pressure. The pressure here is atmospheric pressure. Since they're the same, do you see the water level? How it's equal? Even if this goes down, it's still the same water level because it's the same pressure here and here. Or if I go up, you can even do the little twisty-roo. Water seeks its own level. That's because the pressure is the same. Well, here's a little Fizz keeper pump cap that was designed to increase pressure in here by pumping air into it, and it would keep the fizz from coming out of your soda pop. It actually doesn't work, but it's fun. So if I increase the pressure over here, what should happen? Now the pressures aren't the same. The pressure on this surface of the water is greater than it is over here. And it's sufficient, the difference in pressure, see the height difference? That amount of water. This amount of water down here at this depth creates a certain pressure. That's equal to the difference. Pressure is depth dependent. If you put in the density of water, gravity, and this height difference, it's like a barometer. You can gauge the pressure of the atmosphere. Let's say a storm comes through, the pressure drops. What will happen to this barometer? If the pressure on this side in the atmosphere goes down, what will happen to the water level? It'll go up because there's a bigger difference. This pressure is staying put, it's greater, and it'll be even greater if this drops. So yeah, if this goes up, the amount it goes up can tell you how much the pressure dropped outside. It's a barometer. And if the pressure increases, I can blow in it. I can make it go back down. Or I can suck on it. And decrease the pressure even more. There's actually no such thing as suction. When you drink in a straw, all you're doing is removing the air, which is dropping the pressure in your mouth. If the pressure drops in your mouth, this side, then the atmosphere is greater, and it pushes the fluid up your straw. It's a push. You're not really pulling the water up through the straw. You're just dropping the pressure and letting the atmosphere push it up. Now think of this one. What's the longest you think you could ever have a straw? Could you go forever? If it's the atmosphere that pushes the fluid up the straw, and we know the pressure of one atmosphere, don't we? How much water could it ever hold up? 10 meters. So you theoretically, you couldn't have a straw greater than 10 meters. 10.3, but whatever. Because let's say you drop the pressure completely in your mouth, like to 0 pascals. The difference between the two ends would just be one atmosphere. One atmosphere over here, pushing it up, 0. And the highest it could push water is only 10 meters. So if you ever want to pump water higher than that, you can't do it with just one pump. Or something else has to be going on too. Here's another fun one. Here's a balloon. It's open, but there's a hole in this jar. So you can do this with a water bottle. If you just put a hole in it, you don't need this fancy glass. If I blow this up, it can expand. But what if I plug that hole? Now this container is sealed. You can't, because I'm compressing the air inside, Megan. And as I compress that air, it pushes back. If you give that air a place to go, you can inflate the balloon. But even cooler, inflate the balloon, then seal it. It's still open to the atmosphere. The atmosphere in the room, air pressure, is keeping it open. Because I pushed the air out, sealed it off, so there's less air in there. The pressure inside's less than outside. The air in the room's keeping it open. If I let the air back into the bottle from the room, whoop, pushes it up. I've used this when camping. It was more for fun, but if you put a hole in your bottle, why doesn't the water come out? Because I have the lid on it? But there's a hole. Look at all this water. The pressure is bigger right there. There's pressure from the water trying to shoot it out. So there must be air pressure holding it in. What we've done, when you noticed a little bit of water dripped out right when I opened it? I can squirt some out. But as I do that, the pressure in here drops. And so there's an even greater difference in pressure from the outside to the inside, and that's what keeps the water in. And you're absolutely right. If you now let the air in the top side by loosening the bottle, you can create a shower. Say you had a big one of these that warmed up all day in the tree and you got lots of holes. You soap up, right? And then you go like this and rinse off. Yeah, I know I should be trying to hit the bucket. Now, another thing while I have this one out. Pressure is depth dependent, density dependent. I haven't shown you gravity dependent yet, have I? What if we could get rid of the effect of gravity momentarily? We can't turn gravity off because it's pulling down on it. But what if we let it fall at the rate it's trying to pull down? It would be like it's weightless. So if you do this and then drop the bottle while it's falling, it doesn't squirt out because there isn't that pressure on the inside to push it out. I think that's neat. All right. More fun. Suction cups. This is like your toilet. You're cleaning it out. Plunger. If you push them together, what's it do to the air in between them? Yeah, they actually kind of squish out a little. If it compressed it, you wouldn't be able to do it very much. There you go. And now the air in the room is pushing on the outside, and we can't pull it apart. See if you can do it yourself. And that difference in pressure is exerted over the area of the suction cups. So that's creating the force that we can't overcome. Didn't say it, but it's not easy. If we were to make this bigger, spread that difference in pressure over a big enough area like the hovercraft, team of 8 horses and a team of 8 horses couldn't pull it apart. You let the air back in, piece of cake. They commercialized this. This isn't sticky. There's no adhesive. I got it at a store. It's called a lily pad. It's made out of silicone. Works with rubber. And instead of having to deal with saran wrap to seal your leftover foods, they made this. You just stick it on the top, and it seals it. the air in the room from the top and the bottom over that area is creating the force squishing them together. So it keeps air out from your food. You let the air back in, and it drops. Reseal, piece of cake. Piece of cake sounds good right now. Let's move the air. All right. 8 minutes. Let's start with this one. So I'm going to blow air through this tube. It's open to the atmosphere over here. And it's got water inside these tubes that are connected. They're sealed, but they're open to the tube here, 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 and here. I'm going to blow the air and it's going to start to move. So everything we've learned is true, but you can get a difference in pressure if you start moving the fluid. That can create a change in pressure as well. So let's just show you what happens. This gets smaller. This is bigger. You turn on the air. The pressure increased here. See how it went down? The pressure decreased here because this came up. Just for talking over. Here the pressures are all balanced. It's atmospheric pressure. The air gets in here, pushes on there, pushes, pushes, pushes. It's the same pressure, so they're all at the same height. But so if the pressure increases here, it's going to push harder down here. And it drops here and comes up. Why? The first thing is when the area changes, the fluid speeds up when it goes smaller. This is called the continuity equation. There's two equations to guide our thinking for this. The continuity, and they're in your book. Equation, and it's just A1. This one's velocity, V1, A2, V2. The idea here is, think of all this fluid trying to move through here. The same amount of fluid gets through here eventually. You're pushing the same flow rate. You don't change the flow rate by making it smaller. But if it's smaller, less can get through, right? So it speeds up to get the same amount through in the same amount of time. The flow rate doesn't change. When you constrict the nozzle on your garden hose, you don't let less water out, but it speeds up, doesn't it? As you make the area smaller, if you make the area smaller with your garden hose nozzle or right here, then the fluid speeds up to get the same amount of fluid through in the same amount of time. That's the continuity equation. So here, certain amount of area, A1, V1. It's going at a certain speed. When it enters the smaller area, it increases speed. And that leads to Bernoulli's principle, the second equation. Bernoulli is another scientist's name. And that is, I like how I wrote it down, so I want to say it right. Your book says, where the speed of a fluid increases, internal pressure in the fluid decreases. What's that mean? That means where the speed of the fluid increases, the internal pressure of that fluid decreases. So, the fluid goes faster, there's a corresponding drop in pressure. Fluids in motion exert less pressure on their surroundings the faster they move. Fluids in motion exert less pressure on their surroundings. That's Bernoulli's principle. So these two together, the fact that we change sizes makes it speed up. There's a corresponding drop in pressure, and that's why you saw this come up. Fluids in motion. Up till now, we've just talked about pressure from fluids holding still. But if you start moving them, the faster they move, the less pressure they exert on their surroundings. That's the gist of Bernoulli's principle. That's how airplane wings. You can define an airplane wing that way. As it's moving through the air is moving across it, right? And it gets deflected more on the top than it does the bottom. The speed of the air is different on the top compared to the bottom. It actually goes faster on the top because it's being deflected more. I'll do this demo in a second to show you that. So where air is moving faster, there's a corresponding decrease in pressure. Well, now look, you have a difference in pressure. Higher pressure on the bottom, lower pressure on the top, and that provides lift. That's what keeps an airplane in the air. You can also think of it as Newton's laws. They can explain why an airplane flies also. It's just aerodynamicists prefer to use Bernoulli's principle because it works better. It's easier for them. If you got an airplane wing and the air comes in, it hits it, but then it pushes back on it and it reflects. And there's a recoil. It's like shooting a gun. And that recoil pushes back on the airplane. It's like a rocket. Shoots the fuel out, fuel pushes back. So you can explain airplanes with Newton's laws, but they find it easier with this Bernoulli's principle. Bernoulli's principle is really just conservation of energy. I will give a couple more examples, obviously, on Monday. But let's do this one. Here, it's open to the air at the bottom and the top. This is a piece of styrofoam. If I blow over the top of the tube, I'm going to make the air go faster. And as it hits this, it's like the air gets shrunk. There's these streamlines coming across, and they get squished right there. It's deflecting it. It's kind of like going from a bigger area to a smaller area. It gets constricted there because there's something in the way. Does that make sense? So the continuity equation sort of applies there. You decrease the area, it's constricted, it speeds up. And that has a corresponding drop in pressure. If the pressure drops up here, atmospheric pressure will push on this and be greater than what's being pushed on the top. That's what happens when the air goes over the airplane wing. It gets constricted more on the top. The air that flows over the top goes faster, less pressure. The air on the bottom does not get constricted as much, greater pressure, slower air. Does that make sense? So, just because you got homework, some of the questions will ask you when you got a fluid blowing across something, if it's being deflected by a roof or an umbrella, they're just like these two. One side, probably the fluid's making it go faster because of the continuity equation. There's thus a corresponding drop in pressure. And that difference in pressure can make things move. It can keep airplanes up. It can lift styrofoam. It can raise your umbrella. You know, and when it's windy, have you ever noticed that? Whoa! It's like a curved airplane wing. So that'll help you. All right, have a great weekend. Well, we'll have fun next week.